Hello and welcome to this new episode of Commodore 64 Games Reverse Engineering. I'm going to be reverse engineering a complete game and providing all of the source code so that you can actually use this source code to then create your other games. I'm going to be looking at the Shoot 'em Up construction kit. The first thing we're going to do is have a look at sound effects and emulating what the sound effects do in the original SEERK in the new engine, because we want some nice sound effects while we're playing the game, and we want the sound effects to be basically identical to the original SEERK sound effects. To do this, we need some data offsets in the all data save file, preferably, and we also need some code. And we're going to reverse engineer the code from the original SEERK by disassembling it and then creating something which fits with the rest of the game engine. Basically going to tidy the code. To find the data offsets, as always, we want to save some base data and then modify the data and then look for some binary differences within the file. This is the sound effects portion of the SEERK editor. So the SEERK editor allows you to create different sound effects by choosing the waveform, the attack decay of the envelope for the envelope, however you want to pronounce it, for the sound, the pitch, the speed. You have a rising and falling speed and time, which basically makes the sound effect wibble or wobble upwards or downwards with a different speed. So you can create all sorts of different sound effects. So we're going to save all data, and we're going to save the base data first of all. Then I'm going to go back to the sound effects editor, edit a whole bunch of sound effects. What I'm thinking of doing here is using the copy sound effects option to basically copy altered sound effects, but I'm going to radically change all of the values here. So this started off on a square wave or the pulse wave. I'm going to choose one of the other waveforms. I'm going to change the attack. I'm going to increase it, decay, the pitch, the speed. You can hear actually how the sound effect changes depending on the pitch and the speed and the waveform being used, how the timing alters, how the sound effect updates itself over the frames with the different rising and falling times and speeds. You can actually create quite good variation in the sound effects with this, relatively simple setup. It's not as fully featured a sound effect routine as something you might find in, say for example, my music player, which can also have the ability to play sound effects and interleave them with the music. But this is functionality that you would normally expect to see these days in other music routines, where they can also play sound effects and interleave those sound effects with the music. But this is SEERK, and the SEERK sound effects editor is perfectly functional for the kind of product that it was being positioned at the time. There wasn't an integrated music editor or anything like that, and I think that was perfectly fine. But the different rising and falling times here and the speed is actually quite interesting. I used to love playing around with this sound effects editor way back in the day. Anyway, let's get on with creating the next piece of data so that we can actually have a look for binary differences. So now I've edited the sound effect and changed everything. I want to copy the sound effect from the first sound effect to the next one, which is player 1 explosion. Copy that into player 1 start, player 1 life. What I'm trying to do here is that I'm trying to create a consistently changed starting block of memory in what I'm hoping to find is the sound effects memory. And I'm just creating a larger amount of changed data so that hopefully it's going to be easier to see when I use the binary difference tool to have a look at these two files. We can see that there are four rows and 3 columns. So from that we can work out roughly the kind of like the size of data that we're expecting to see. So we can assume that we're going to be seeing 24 sound effects in memory. So we note that down. Now let's see if we can find a suitable number of bytes being changed with this binary difference, and I'm pretty sure this looks like a good start, doesn't it? I don't think it's this memory range because that's way too far down at the end of memory, or nearer the end of memory in the last Vic bank. So here looks like the only really viable choice, because there are so many bytes that have been changed and those bytes aren't anywhere within the graphics memory or anything like that. I think this is an excellent candidate. So the file offset is AF2C, but we need to convert this into a memory offset because the macro, which imports the data, uses the memory address range. So we subtract 1C and we add on 900 in hex, which gives us the final memory address of B810. The first video goes into more detail why 1C is subtracted in hex and then 900 is added on in hex. So refer back to the first video if you want to understand why more. But basically the file that's saved out from the emulator is a data file with some extra header information. It's not a straight memory dump from the Commodore 64, and we want the memory address on the Commodore 64. So to find the code, what we can actually do is that we can use the monitor in the emulator to look for writes to the SID chip, and the SID chip starts at D400 in hex. So if we do a watch store D400 and we go into the sound effects editor, we've hit our first breakpoint, and the routine looks like it starts at 5C09, and that's just because it's after the last RTS. Up there we go, that's where the breakpoint is. So 5C09 looks like an initialization routine. The code is storing 8 into the first 3 voices and their waveform control, and 8 basically sets the test bit with the gate off, if I remember correctly, and that basically causes the voice to go silent. It means that you're initializing the SID so that the voice, all 3 voices are nice and silent. There's also an initialization there for the volume, which is at D418, and it sets that to 15, and then it does an RTS. It also clears all of the SID voice channels. It's also clearing some 0 page locations as well. It's clearing quite a lot of the 0 page locations. So we need to find, in this code reverse engineering, we need to find the initialization function, a typical play function, which probably uses a register input to signify which sound effect you want to play, and then a tick, which you have to tick. You have to call the tick function usually every frame to actually update the registers in the SID chip with all of your calculated sound effects. So I'm taking some guesses here, but these guesses usually, they look pretty much correct, right? The routine at 5C33 is just after the RTS from the initialization routine, which is at 5C09, so we'll note that one down. That looks like a valid entry point for the play sound effects routine. We can test this a little bit later on, but this looks all pretty much straightforward code. And then after the play sound effects routine, there is an RTS. There are some temporary values being stored in the memory there, and then it looks like that's the tick routine after there, where it does the load accumulator. So this load accumulator routine, which is at 5C94 here, which looks like the tick routine, that's being called every frame. I think we can safely assume that that's doing the necessary tick that we want to see. And if we start a sound effect, there we go, the accumulator is 0 and it's coming into the routine at 5C33 there. If I choose a different sound effect, like the 7th one or the 8th one in the list, counting from 0, we've got accumulator with 7, accumulator is now 8, so enemy fire starts at 8. So I'm pretty sure that this is the play sound effects routine, where the accumulator equals the sound effects number, 0 based, of course, to play the sound effects which are in memory. Now, we don't need to precisely understand the bytes as they are stored in memory for each of the sound effects, because we'll be taking all of this code, disassembling it, and then pretty much using it verbatim, but basically tidied and using the label names and everything else that we want to use, and probably different memory location storage for its temporary working area as well. We don't want to use too much of 0 page, for example. We can see how much memory is being used by this routine by using the memmap zap command, which clears the memory map for memory accesses. SEERK has this nice little jump table at 4000 in hex, containing all of the relevant jumps it needs to use to get into the relevant different sound effects routines and sprite routines and all sorts of editor screens and stuff like that, which is quite nicely laid out. But we can see when we return from this routine that this is the last memory address that was read from, the 5D64. So 5D62 looks like the end of the code for the tick routine, and we know the start of the initialization routine at 5C09. So the memmap zap and the memmap show commands that I was using there in the emulator's monitor basically shows which memory locations are being executed, where the code is executing from, or where memory has been read or stored. And this is an extension a very good extension to the emulator's monitor, where I can basically see where the CPU has touched on various different pieces of memory, and this allows me to narrow down where the memory ranges are for particular routines that I want to have a look at, or anybody else wants to have a look at, to be honest. It gives you a good feeling about how large a routine is, because if you let the routine run, right, and it's accessing code within this memory range from start of memory to the end of memory somewhere, then you know that you want to disassemble that piece of memory and have a look at it in more detail. And it enables you to see whether or not the code is calling out to other code elsewhere which is distant from where the sound effects code is. So, say for example, it might have been calling to a different routine somewhere in the editor, and you want to make sure that you also disassemble that routine as well and to understand it. So what I'm doing now is that I've restarted the emulator with SEERK, but now I have attached my Vice PDB monitor, which is a separate application, it basically connects to the network address for the emulator's monitor rather than relying on the monitor window itself. I'm doing this because I want to use my tool to disassemble the code, because then I can copy and paste from the disassembly of code window in the bottom left hand side here. So all of the command outputs and everything like that, all of the results from the commands appear in the bottom left hand window. You can also see that I've got the register view up in the top left as well, so when it hits the breakpoint it refreshes the registers automatically. But what I want to do is that I want to make sure that I can disassemble the code. So it will automatically disassemble a small amount of the code anyway when I'm single stepping, or if I choose to step into or out of functions and stuff like that. But it also allows me to send commands to the monitor, so that then I can disassemble the code as I see fit. Here I'm doing a memory map and then a memory map show, MMSH, which is the short version of memmap show command. And this just lets me scroll up and down the full memory map view of the code that has been touched. So for example, when I am calling the sound effects play routine, or rather when the editor is calling the sound effects play routine. So I can verify the output from the memmap show command a lot easier by using this window compared to the emulator's monitor window. The emulator's monitor window has a limited scrollable history. In fact, it doesn't really scroll at all, right? So I want the scrollable history, so that's why I'm using my tool, which connects over the network to the network interface of the emulator's machine code monitor. So these are the three entry points that I'm interested in, right? I've added those breakpoints by using the BK command, which is an abbreviation of the break command, BREAK. You can see here 5C94, when it is called, accesses this extra memory as well just after the sound effects routine, but it's also storing into the SID registers at D400 down here. Look, you can see those. I'm highlighting them there. So you can see the SID registers that are being updated by the tick routine. I'm interested now to disassemble the entire sound effects routine. So it's starting at 5C09 and ending at roughly 5D61 inclusive there. To make it easier to read the code, what I want to do is that I want to populate it with labels. So when I'm going to be reassembling this disassembled code, it's going to be a lot more readable and understandable if I use some sensible labels. That's why I'm loading the label file there. So when I do the same disassembly, which I just did before, so there we go, 5D62. There's actually a command history, but the drop down doesn't seem to include it there, which is really quite annoying, but hey, there we go. So now when I do the disassembly, it's actually including labels for, say for example, the SID routine, the SID registers in the SID chip. Not all of them. D3FF is 1 byte before the SID chip, so it's not recognizing that as a valid memory address to put a label for. Okay, but the other SID voice, that's SID voice 1 attack decay, SID voice 1 sustain release, voice 1 control, for example, those are all valid labels. And we can see there B810. B810 is the memory address for the sound effects data that we saw coming from the binary difference that we just did between those two files. So now we have what looks like the whole of the sound effects code. The sound effects initialization, the play sound effects function, and the sound effects tick routine, which is what we want to call every frame. So now we have enough information to pull in the data from the data file and also the code for the sound effects routine. We can then create a nicely tidied source file for the sound effects play and apply some various different optimizations, and also using different temporary workspace or working area, if you like, for each of the three voices that are in the SID. So the sound effects can occur on each of the three voices for the SID. So there's some temporary working area and stuff like that. But basically, we can compare the original SIG code with the replacement code, and it's functionally pretty much identical, except that it's just had some optimizations applied here and there and some tidying up in terms of the labels being used and so on and so forth. The ordering of some of the initialization has been changed compared to the original SIG code as well, but basically the initialization routine is functionally identical. The voice 1 control has been changed so that it does it there, for example, rather than at the beginning of the routine. The sound effects play routine there, so this in the original code it does a shift, store, two shifts, a clear carry and an add, and a transfer accumulator with Y. Those shifts and adds are effectively multiplied by 10. So instead of doing the shifts and adds, when it basically shifts once, which is a multiply by 2, shifts by a further 2 more shifts, which is a multiply by 8. So then it's adding together the multiply by 8 and the multiply by 2 to get a multiply by 10. Okay, I didn't like that approach, so I actually had a sound effects index multiply by 10 table. So I used a table in the replacement code compared to doing all of those shifts. Looking up into a table uses more bytes for the table storage, but it's actually a lot quicker than doing a whole bunch of shifts. For example, the multiply by 10 is there because there are 10 bytes, I think, for each of the sound effects storage, right? It just wants to look up into the data table. But basically, the code is tidied but functionally identical there. We can see there's some initialization and some global counter updates being done. And then there's this process voices function, which is called 3 times with different entry values. So these different entry values are basically different offsets for SID voice 1, SID voice 2, and SID voice 3. And the SID voices are laid out in terms of registers in the memory address layout. They're laid out in regular blocks of registers for each voice. So that's why you can use the same code but with different starting offsets to update the voice. So you can reuse the same functional code to update 3 different voices just by using different starting update offsets. Anyway, so this sound effects code can be included, of course, in the full SEERK Redux replacement engine, but it also can be used as a standalone piece of code, like many of the other pieces of code that are used in the engine as well, like the multiplexer can be used, like the scroller can be reused. So this test SFX source file can be assembled along with the sfx.c replacement assembly file, and then you can see that it outputs a PRG, which is a self standalone program file, which allows you to press the fire button and then hear all of the different sound effects. And all of these different sound effects come from one of the example game files, example game number 3 from the original SEERK distribution. So we can pretty much see now, or hear rather, that the replacement sound effects code works in isolation. And so the sound effects code can then be added to the game engine. So we've got the sound effects SID init function, which we need to call when we start the game. Then there's the SFX init, which is basically what sound effect to play. And we can see that it's been commented with the input accumulator A equals the sound effects index, right? So all throughout the code, there are all of these different events. The enemy firing, the player explosion, enemy explosions. All of those get fed, although all of those events with the different memory for what sound effects index to play in what particular events are sent to the SFX init function, which initializes the relevant sound effect with whatever value is in the accumulator. So we know that player fire is index 0, player 2 fire is index 4, for example. We know what sound effects to play when the player hits an enemy bullet, for example, when the player dies, when you get extra lives, so on and so forth, when there are enemy explosion sound effects. All of these are identified values that were identified in previous videos for different animation events. Either in the animation, so we're looking in the animation engine.a file there, which is the core animation engine for how the SEERK animation data is interpreted. So when a new enemy is spawned, we store the enemy's sound effects index values, we store those into the animation routine or the animation engine's data storage there, so that when an enemy explodes or when an enemy fires, the animation routine knows that that slot that's currently being used for an enemy animation can then play the relevant sound effect. So all of this work is basically tying in all of these known values that were discovered in previous videos from all of that reverse engineering, and then plugging them into the sound effects initialization routine, the sound effects, which sound effect to play routine. So all of these events are all just tied together. So all of this work that had been done previously to reverse engineer all of these values for all of these different events are then just plugged into the final sound effects routine. So the beauty of doing all of this preparation work is that actually it's pretty quick and simple to plug in the final sound effects routine to get it to do all of this stuff, because all of the preparation work had been done previously in the previous videos. For future reference, I'm just adding the remote monitor command line flag to those command lines there, just to make it easier to attach the remote monitor later on if I need to. The remote monitor is the machine code monitor with the network interface, which allows that Vice PDB debugger to be attached to the monitor. So you can hear now, as I play the game, the different events like the player spawning, the player firing, the enemies firing, the enemies exploding. All of those sound effects events are plugged into the game, and it sounds a lot better now, right? The game is not silent anymore. The game actually includes sound effects, which is really quite cool. And of course you can take that source code and you can use it in your own games projects. You can improve the sound effects. You can change the sound effects. You could, say for example, use a music player routine which has much better sound effects, and you can use that instead. But the idea behind this game engine reverse engineering series of videos is to basically show you how to put all of this stuff together, to go through the whole process of how to reverse engineer something and then create functionally identical code. So the next thing that we're going to look at is that we need to finally finish the reverse engineering for the title screen. Now, the character set for the title screen had been found in the previous video because that's the character set that's used for the score. However, we need to find where the text and the color effect information is located. So we need some base data again for the title screen reverse engineering now, or the title screen text reverse engineering. So we'll save that. I just want to show you what the front end stuff looks like. So we're looking for the message. Okay, so we're looking for this message that gets displayed on the screen. We can use the editor to add and remove different text, right, just by typing it. And the data that we're looking for is going to be quite easy to find, but we still need to go through those steps, nice and logical. So there's the base data that's been saved out. Now the base data has been saved out, we want to edit the message text, so we'll just put in a whole bunch of repeated characters. Again, the idea being to change quite a bit of data so that we can look for the start and end of the data in the all data save file. So I put some A's at the beginning and I put a load of B's at the end of the editable screen for the title screen area there. So now we can have a look at the binary data to try and find that text screen. And we'll use the binary difference tool that we always use for that. We also have this notion of changing the message color effect. right, in the editor, which we also need to find. The first 15 message color effects are static colors, and then the rest of the color effects after 15, so 16 onwards, are these scrolling raster bars, which are behind the text. Now, the first 15 color effects basically mirror the colors in the VIC, in the video chip. Okay, so color 1 is white, color 2 is red, for example, so on and so forth. But we want to make sure that we can replicate fully the raster bar effect, right? So I'm thinking that we use the same approach as for the sound effects, and we try and reverse engineer by looking at the code. So we put a watch store at D021. D021 is the VIC2 screen color. Now the screen color is being used for the raster bar effect here. The screen color shows through the transparent pixels of the text character set. And when we inspect this code, what do we see? Well, we see a load accumulator with 0, 5, y there indirected. 5 and 6 in the 0 page point to memory address 98BB. And it's indexing that with y, and y seems to cycle around between the values of 0 and 7 there. It's doing an increment y, transfer ya, and with 7 ta back again, which is a transfer accumulator back to y. It's then doing 2 increment x's. X is being used to compare with D012. D012 is the VIC register for the raster position. So the raster position starts there with load x with 62 at 9793, and then it loops through 2 raster lines for each iteration and stores into D021 the color, the target color, which is used for that particular raster line for that particular color effect. There at 41C6, look, there is a load A with 409C, and also if I choose a different color effect, then look, the memory address is different. That's the memory address being used in the title screen editor. I think we need to look at the memory address that's being used when actually the game is being prototyped rather than the title screen editor itself. That memory address is different, right, to the previous memory. It's wildly different. So I think we need to double check that. But basically, this code is looking at 409C, which is at 416, at memory address 4162 there, look, load accumulator with 409C. And 409C, then it does a compare with 16. So this looks like it's checking whether or not to load the value from the indirected table, y, or just using it straight as storing it into the screen register D021 there. So when we test the game, you see it's different. The memory address being used for that indirected indexed table is different. So depending on, see, it was 41C1, now it's 41C9, and that's after I changed the color table effect by 1. So it seems that we have 8 colors for each of the raster bar color table effects. Yep, okay. This routine here seems to deal with updating those values, but it was doing that update, the one pixel color shift, it was doing that every 4 frames for the color bar scroll as well. All of this is useful information to know by looking at the original code so that it can be replicated in the replacement code. We can see here, look, it's doing a load accumulator with 409C, subtracting 16 or 10 in hex and then multiplying it by 8 there, those 3 shifts, 2, 4, 8, yeah. It's multiplying it by 8 there and then adding on the low by into and storing it into 5 and then incrementing 6 if the carry is clear. Yeah, this is classic. This is classic raster bar animation update code. Basically, it's calculating the table to use for the raster bar effect, for the indirected raster bar effect, pre-calculating it. So we know now where the raster bar color data information is kept. It's, say for example, 41C1, and we know where the raster bar, where the byte in memory is, which signifies which color effect it uses, 409C. So we can extract that from the all data save file. 8 entries per effect, right? And the effects start at 16 or 10 in hex. So you're right. If you have been thinking this, yes, the raster bar color effects are saved out in the all data save file. And that's because the all data save file is basically like a snapshot of almost all of the data in memory. So yes, the all data save file is quite wasteful, but it is comprehensive and complete. It means that if you have a slightly different version of the editor, if it loads up the all data save file, it means that you get that version of the editor basically back again, almost. Although I don't think that there are too many different versions of Circ. There's a horizontal version of Circ, but we're looking at the vertical version of Circ at the moment. The horizontal version of Circ is actually memory compatible, practically, with the vertical scrolling version. But yeah, to putting a breakpoint at 409C and then changing the color effect in the editor causes the breakpoint to get hit. It's not really important for the reverse engineering sequence of videos, but basically the editor seems to have a nice little callback mechanism. So when a value is tweaked in the editor, it knows that it needs to map that tweaked value back to a memory location, and it seems to do a lookup for that. So now if we do a binary difference for the text, here it's very obvious, right? The text is even viewable in the binary, the file binary difference viewer there. We can see that start address is 2920. In the file, we need to convert that back to a memory address. So 2920 minus 1C plus 900 is 3204 in hex. That's the memory address that we need to extract when we are importing the text to render for the title screen. Now, the title screen itself is, the title screen code itself is pretty simple and easy to understand. All it needs to do is basically initialize the screen, copy over the character data, copy over the character set data into the relevant places for the Vic chip to render, and then replicate the raster bar effect. And we know the code for replicating the raster bar effect already, so that can also be used as a reference for the new code. So we will have all of this useful information here. That's all perfectly fine. Just updating the document here for future reference, just in case. So the title screen code uses these values here. So the title screen chars are basically the characters that are pulled in for the text on the title screen. The raster color table looks at memory address 41C1. The raster color table type, which is the title screen effects type, is 409C. So the title screen code and in title screen.a, right, basically pulls in all of this data and does all of the memory copying and does all of the color bar, raster bar updates, as you would normally expect. The exact nature of how to do raster bar updates is basically you time the writes to the Vic register for the screen or the border or the border register for those colors, and you time those as the raster bar is traveling down, as the raster beam is traveling down the screen. As the Vic drives the raster beam, we can time the code to precisely update those register color values, and then the colors are updated in the rest of us. It's actually a very simple routine. Once you get your head around understanding how fast machine code is, you know that you can update a fair few number of registers in the display chip or in the VIC chip or in the SID chip to do all sorts of different effects. But here we're just doing a very simple effect, which is a raster bar effect. And we basically have the code here in titlescreen.a, which basically replicates the functionality of the original SEEIT code quite comprehensively. So when we assemble that code and have it all including the new title screen code, then we get the title screen, which is in the new engine now in the replacement code. So the color bar effect is the same, the text copy is all the same. You can pause the game, quit back by pressing the Q key. You can also quit back by hitting the restore key. Goes back to the title screen. Everything is great. Now we have a complete engine. So the complete engine, game engine, includes all of the functionality of SEEIT and replicates it all. So you have access to all of this source code. Now, I actually added a little bit of extra tweak here for the title screen. So I wanted to add animating sprites. So adding animating sprites to exercise the multiplexer on the title screen. If you know Commodore 64 games, then it's actually quite a familiar sprite pattern. You might get a hint here from the file that I was pulling in there, and it's basically the Armalite balls. So if you have Armalite, or if you're familiar with Armalite, then Armalite have little patterns of balls, or very nice patterns of balls actually, which grow and shrink in size, like a perspective effect. This is the beauty of having code which you can edit yourself and expand yourself, is that you can get SEEIT to do all sorts of extra stuff that it wasn't really, feasible to put in to the original SEEIT engine. So this is the new code running a familiar sprite attract sequence, which basically has a whole bunch of rotating sprite-based balls, which is from the Armalite introduction sequence. The sine and cosine table, well, the sine table that's being used for the ball pattern is actually not from Armalite. It's actually different. It's actually two interleaved accurate circles which are being used there. It's not using the evenly spaced sprite trick, moving sprites up and down in even spaces. Actually, it's using properly spaced circles, but basically it's a very similar looking effect. You can also, say for example, include music in the title screen by disabling the scroller no music label there. It pulls in a music file as well and assembles that in with everything else and plays music on the title screen. So all of this is pretty easy to understand code. If you're any kind of like coder on the Commodore 64, this should be quite easy to understand code. And I think we'll leave this video there. There's already quite a lot to get into. The next video will probably include the last updates for different parts of the game engine that can be customizable. So say for example super weapons and stuff like that. But we'll get into that in the next video. So thank you very much for watching. If you like these kind of crazy retro games, reverse engineering deep dive sessions, then please do consider liking or subscribing to this channel. And if you really like the work that I do, then a super thanks is always very welcome. Thank you very much for watching. Take care. Have a great day or evening wherever you are.